Friday. Welcome to the Tejano Virtual Events Happy Math Hour, our weekly interactive math review for Math 1314 and Math 1324, presented by Yvette Chuca, Ruben Carrizales, and Albert Isasi. Our session will be starting soon. This session will be recorded so that you may come back to it later if you need, and so others who may have missed out on today's events will be able to come and watch it. Thank you. So now at this time, please mute your mix for best sound experience. Otherwise, the feedback could interfere with information we will be sharing. We'll be sending the 1324 room link on the chat so that you may connect to your session if you are here for Math 1324. Mrs. Patricia will be sending individual messages to everyone to gather your student ID numbers to sign you in. Without further ado, please, I'll pass it on to our presenters so that we may begin.
Good morning, everyone, and thank you for joining us at today's Happy Math Hour. Again, if you are here for Math 1324, you'll see the link here for the Math 1324 in a little bit, I believe. Let's see. I think that's the link for the Math 1324. So if you're here for Math 1324 on the chat, please go ahead and go on that link. If you're here for Math 1314, today's session will be going over basic matrix operations and using matrix operations. All right, so let's go ahead and get started. So what we're looking at here is section 8.1, which we're going to be dealing with matrices. Yes, okay. Dealing with matrices. So what is a matrix? A matrix is a rectangular array of numbers. Now, the way we represent matrices is with these brackets, okay? And the numbers inside our brackets, we're going to call them elements, okay? So here, this is the book definition of a matrix, and again, it's an array, rectangular array of numbers, and they're ordered in this particular way, okay? A matrix is going to have rows, okay, and it's going to have columns. So each entry, again, in our matrix is called an element in this matrix. Now, here, if we look at the elements, okay, the elements here are described as the position is described as a suffix here. This number 1 is not 11. This means row 1, column 1. For instance, this number, the second one here, A12, that means this element is in row 1, column 2, and so on and so forth. Okay. All right, so when we are looking at the size of a matrix, we call this its dimensions, and the dimensions are going to be crucial when we're doing operations with our matrices. Okay, so the way we determine what the size of a matrix is or what the dimension of a matrix is we label it by the number of rows by its number of columns. So for instance, in our first example, we have 2 rows and we have 2 columns. So the dimensions of this matrix is a 2 by 2, or the size is a 2 by 2. Okay. If we look at the second example, we only have 1 row and 2 columns. So the dimensions of this matrix is a 1 by 2. Okay. So the first one, if I go back to the first one, our 2 by 2, the reason why this is called a square matrix is any matrix that has the same number of rows with the same number of columns is called a square matrix. So if I would have had 3 rows and 3 columns, that would have also been a squared matrix, okay? 5 rows, 5 columns, that is also a square matrix. So a square matrix is anything that has the same number of rows with the same number of columns, okay? All right. So now let's, so this one that only has a row, just 1 row, we call this a row matrix. Now the second one here, we see we have 2 rows, but only 1 column. So when we have only 1 column, we call this a column matrix. And again, the dimensions of this matrix is a 2 by 1. And please don't forget, we always label our matrices, or our size, our matrix is always the rows times columns. We have to keep these order, rows and columns. All right, and then the last one is a square matrix again, because we have 2 rows and 2 columns, but this one's called an identity matrix. The identity matrix is whenever we have this 1 0 0 1, and what this is telling you is you can think of this as the value of 1 for the matrix. And again, we'll go in more details on this matrix. All right, so let's go through this problem and determine the dimensions of each of these matrices. So let's start with A. A, we see we only have 1 row and 1 column. So what would the answer be for this one? So the answer for this one would be, oops, we're missing the, I guess I have to draw it myself. So let me draw this. So for A, if you see here that I have 1 row, 1 column, well, which one is for this one? So A is G, right? This one right here. Okay. All right. So maybe this is not a good idea because it's going to block. Let's just do the B. So B is 1 row, but I have 1, 2, 3, 4 columns. So the dimensions of this matrix is 1 by 4. So where do we have 1 by 4? This is C right here. So B is, for this one, C. C has 2 rows and 2 columns. So this one would be B right here. 2 rows, 2 columns. And then the last one, D. D, we have 1, 2, 3 rows and 2 columns. So the dimensions is a 3 by 2. So that one would refer to the D itself. Okay. So this is how we determine the size of a matrix, or the dimensions of the matrix is the rows times columns. Okay. All right. So now what we want to do is you saw in chapter 7 we were dealing with linear systems, right? Well, now what we can do is we can convert a linear system to what's called a matrix system, but it's a special name. We call it an augmented matrix. So to do this, to convert a linear system to its augmented matrix form, okay, you're only going to get the coefficients of the equation. So for instance, this is this linear system. If I see this line 1, line 1 is 3x plus 5, 1 is equal to -9. So the coefficient of x is 3. That will be here in my position, row 1, column 1. My 5 will go in row 1, column 2. And then the way we represent the equal sign in an augmented matrix is just by this line. Okay, so our line is represented by the equal sign. So equals, and then it's just our solution, the -9. So then my line 2, again, I'm only going to grab the coefficients of the variables. So here x is 1. So this 1 is in the position row 2, column 1. So that would have a suffix of 2, 1, right? The 4 for the y. So that would be in row 2, column 2, right? And then again, the line is represented by equals, and that the solution is -10. So what I just did is I converted a linear system into a matrix system. And again, the name of this is called an augmented matrix form. Okay. All right. So let's practice. Let's convert this matrix, this linear system, into its augmented matrix form. Okay. So first, let's find out what is the dimensions of our augmented matrix, right? Or we'll do that at the end. So here, if we see, we have 4 variables, right? We have x, y, w, and z. So we're going to write them here, x, y, z, and w. Now, I would have put the w first, but it doesn't really matter, okay? So the z and w. And then our constants, our solutions, are going to be to the right of this line. Again, this line is represented by an equals, okay? So when we do this, let's go ahead and do our augmented matrix form. So here on this line 1, we have a 1 for x, we have a 3 for the y, There is no z, so when we don't have a variable here that represents, we represent it as a 0. Okay, so it's like our placement value. And then our w would be a -1 equals 9. Now let's do line 2. There is no value for x, so again, x would be 0. Then y, we have a -1 here. So again, we're just putting in our coefficients. -1. We have 4 for z, so that would be just a 4. We have a 2w, so that would be just a 2 here, equals the -2. Now line 3. Line 3 here for x, we have a 1. Now there's no y here, so we're represented as a 0 in our column here. So this would be row 3, column 2 would be have a 0. And then we have a -5z, so we just put a -5 for the column of the z. Then we have a -6w, so we're going to put a -6 for the column of the w. And this equals 0. Then we go to our last one, our last line. So we have 2x, so that's 2 for the column of the x. We have a 4y, so that's just a 4 for the column of the y. We don't have, we have a -3z, so we have -3 for a column of the z, and we don't have a w. So we represent it as 0 equals 4. And again, to represent that we are dealing with a matrix, we use brackets to represent our matrices, yes? So then to answer the question, what are the dimensions of this augmented matrix? We have 1, 2, 3, 4 rows, and we have 1, 2, 3, 4, 5 columns. So the dimensions is a 4 by 5 matrix, okay? All right, so let's look at something copied out of your homework. It says, write the system of linear equations represented by the augmented matrix. Now we're going backwards. So again, on the computer, they represented the equal as 3 dots. Okay, so if we were doing it on paper it's just a line, but on the computer, you're gonna see the equals as just these three dots. Okay. So again, we want to go from its augmented matrix form now back to a linear system. So we see here, we have 2 columns. Just like before, when we were writing our variables, we had 4 columns. We had the x, y, w, and z, right? So in this case, as we have only 2 columns, we only have 2 variables. So our variables are going to be x and y, okay? So let's go ahead and do it. So from our first line, or our first row, we have a 6, so that would be represented by the 6x. The element in row 1, column 2, the 5, that would be in the y, so that would be a 5y. And since both of these are positive numbers, they're being added, so that's why it's +6 and the +5. Again, the 3 dots mean equal, so equals 2. So there is my line 1. Now line 2. Line 2 here in row 2, column 1, I have a 3. So that refers to my +3x. My row 2, column 2 element, the -9. Since it's a -9, that refers to the -9y. And then again, our dots equals, it represents our equal symbol. So equals 0. So now I was able to go backwards. I can get an augmented matrix and rewrite it as a linear system. And again, we write the linear systems with only the one bracket on the left, the squiggly bracket, okay? All right, so let's practice. Write the system of linear equations represented by its augmented matrix, okay? So again, on this one, I don't see the dots, so I'm just going to represent this as this. So if you see here, if you remember as before, this is our identity matrix. So another way you can think of this identity matrix is that this is like the solving for the x and y intercepts. If this is the position for x, then there's telling me that I don't have a y value. And if I don't have a position for, if I have a 0 for x, then this means that this is my y value. So this is another way we can represent our intercepts, right? So this is my identity matrix. So what this is saying is that the x value equals 4, and the y value equals 3. Okay. All right. So now let's go into using matrices to solve linear systems. So there's several row operations that we can do to do this. So one of the things that we can use is to interchange two rows. And the syntax to represent that we're going to be doing this is by this double arrow. And what this says is that I'm going to replace row A with, or interchange row A with row B, whatever those are, right? We interchange them. Another elementary row operation that we can do is we can multiply a constant to a row, okay? And the way we represent this is this, the C. I can multiply a constant, a number, to a row. And you got to keep in mind, these equations or representations on a matrix came from lines, so, or equations. So we got to make sure that we multiply that constant to both sides, to the left and to the right side of the zero. Okay. And then we can add multiple rows together. We can add one row to another row, and the syntax for that is in this format. And you're going to see why we want to do this. So if you remember, if you recall from chapter 7, when we're doing linear systems, you learned how to solve linear systems by the addition method and the elimination method. Well, these operations here that I just described is kind of putting those two operations together, but now we're going to use them for matrices. And the best way to get this is by seeing an example. So let's go to it, okay? So here, we have a linear system, 6x plus 5y equals 2, 3x minus 9y equals 0. And the first thing that we want to do is we want to convert it into its augmented matrix form. So again, we've done this already. So this linear system in its augmented matrix form would be, again, we're using brackets for our matrix, and it would be 6, 5 equals 2, 3, negative 9 equals 0. We're not including the variables, we're just putting in the numbers, okay? Now, to solve a augmented matrix form, we're going to do basic operations, and what we want to do to solve is just like that previous example. We want our left side to look like our identity matrix, the 1, 0, 0, 1, because this is telling me I'm going to get the x value and the y values of the equation, okay? So the process to go from our augmented matrix form to this 1, 0, 0, 1 on the left side of our matrix, it's called reduced echelon form, and we're going to do row operations. So some books call it Gaussian elimination or Gauss-Jordan elimination, but these are all mean the same thing. We want to get into this form, which is reduced echelon form, to solve for our x and y values. All right. So let's look at this example. Let's do first practice the operations, and then we'll solve for one completely. Okay. So to go over the A, when it says interchanging the first row and the second row, okay, the reason why we want to do this is, again, we want to have our matrix have a 1, 0, 0, 0, 1, 0, 0, 0, 1. We want an identity here. So we have all ones for the indicated variable. So in this case, since we have a 3 by 4 matrix, we have 3 variables. We're going to have an x, y, z, right? So here, since the first one here on the top is 0, but we want a 1, we can interchange row 1 and row 2, so we can have a 1 in the beginning, and we don't have a 0 there at the corner. Okay, so that's one representation on how we would interchange two rows. And again, all of the variables change. All the variables in row 1, negative 1, 2, 0, 3, become now row 1, negative 1, 2, 0, 3. And the elements in row 1, the 0, 1, 3, 4, become all of the elements in row 2. So now that's 0, 1, 3, 4. Okay, so this is an example of how we interchange rows. Okay, so to give you an example on how we can multiply a constant to a row, let's say that my original line here is this value 2, -4, 6, -2. But because I want a 1 here in the first position, what I can do is I can multiply a 1/2 to row 1, and the syntax is here. And again, if I'm going to multiply the 1/2, I'm going to multiply to all of the elements in that row. So when I multiply 1/2 to row 1, my new row 1 becomes 1/2 times 2 will give me a 1. 1/2 times a -4 will give me a -2. A 1/2 times 6 will give me a 3. And a 1/2 times a -2 will give me a -1. So this is an example on how we can multiply a constant to a row. Okay. And now let's do the last one, the C. The C says that we can add 2 rows together by multiplying a constant, so we can eliminate the number. So for instance here, in row 3, I would want this row 3, for my row 3 column 1 value, there's a 2, but I want that to be a 0. So what I'm going to do is I'm going to look at row 1. Oh, row 1 has a 1, and if row 1 would have a -2, and I would add it to this 2, I would get a 0 here. So this is what I'm going to do. The syntax would be, I'm going to multiply -2 to row 1, and I'm going to add it to row 3 to get a new row 3. So let's do this, and we're going to do these in our heads. Okay, so if I multiply -2 times 1, so that's a -2. -2 plus 2, that's 0, and that's what goes here in the row 3, column 1. Now let's do the next one. A -2 times a +2, that's a -4. -4 plus 1 is a -3, and that's what goes here in row 3, column 2, the -3. Now let's do the next one. A -2 times a -4, that's a +8. 8 plus 5 is 13, and that's what goes here in the row 3, column 3. That's my value, 13. Now the last one, again, I have to do them to all of the elements. This is the solution. This is the equals, but I still have to do it to that one too. Okay, a -2 times 3 is a -6. -6 plus a -2 is going to give me the -8. So that's the -8 here. Row 3, column 4 position, that's what goes there. So this is an example of how we can do that third basic row operation, multiplying a constant and adding it to another row to eliminate the value. Okay, and if you could see, this is just the elimination that we learned back in chapter 7, but we're not using the variables, we're just using their constants, right, or in the matrix form. All right, so let's go ahead and do an example. Use matrices to solve the system. So we have our system is composed of 2 lines, the 2x plus 4y equals 8, and the x minus y equals 5. So the first thing I need to do, since it says use matrices, I need to convert this linear system into my augmented matrix form. All right, so here I got the 2, and I put it in the first row, row 1, column 1. The 4 goes in my row 1, column 2. Again, we write a line, means equals 8. And then my row 2, the value here is a 1, so that's row 1, column 1 is the 1. I have a -y, so that's a -1 in my row 2, column 2, equals 5, right? So I converted this linear system first into my augmented matrix form. So then our goal to solve this is to have this matrix look like this: 1, 0, A, 0, 1, B. So again, this A, B is going to be the solution of the X and Y. Okay, so let's go ahead and do this. So the first thing that I'm going to do, now this is not necessary, but we're just going to go ahead and practice. We can interchange row 1 and row 2, just so I can have a 1 here. And again, this makes our life easy, right? So the row 1 now became my row 2, now became my row 1, and my row 2 is my row 1. Yes. So I have now this 1, -1. Again, I forgot the little line here. don't forget this is equals 5. And then we have 2, 4 equals 8. Okay. All right. So the next step is we want a 0 in my row 2, column 2 position. Where the 2 is, I want a 0 there. So, and keep in mind, we want to follow this order. We want to go column by column. Don't skip, because if you do, you'll go in circles. You want to always, when you're doing your zeros, you want to go column by column. All right. So now, since I want a 0 here, I'm going to multiply a -2 to row 1, add it to row 2, and that's going to give me my new row 2. Okay. So let's go ahead and now I have it on. We don't have to do it in our heads. I wrote them down, right? So here I multiply a -2 to row 1. So it's a -2 times 1. And I'm going to add it to the row 2, 2. So a -2 plus 2, that's 0. That goes there. Then I'm going to multiply a -2 times the -1. A -2 times the -1, that's going to give me a +2. And when I add it to 4, that gives me 6. That goes in my row 2, column 2. Then, one more time, I'm going to multiply -2 times the 5. -2 times 5 is 10. I'm going to add it to the 8. -10 plus 8 is -2, and that's equals -2 on my row 2. Okay, so I'm almost halfway there. On my column 1, have a 1, 0. But now on my column 2, what I want is a 0, 1 here. Okay, now so what I'm going to do is I'm going to multiply row 2 by a 1/6, so I can have the 1 here. Okay, now I'm going to go ahead and do it, but you're going to notice something. So let me go ahead and do this operation. Now, another thing that I want to mention to you is, do you see that I wrote the syntax here? 1/6 row 2 is going to give my row 2. I'm changing the appearance of my row 2, but I am not doing anything to my row 1. So it's very important that I like to write the rows that are not getting affected, the ones that I'm not doing anything. I write that first before I start doing anything, because I can easily forget what row am I working on, right? So here, I'm going to multiply the 1/6 to the row 2. So 1/6 times 0, that will give me 0. 1/6 times 6, that's going to give me 1. And the 1/6 times the -2 is going to give me a -1/3. And again, I didn't do anything to my row 1, so I leave it alone. 1, -1, 5. Now, if you notice here, my solution, I got a fraction, and if I'm going to eliminate the other stuff, I'm gonna have to be working with a fraction. So I'm just gonna work with it just so you can see that I can do this. But what I like to do first is I like to get the zeros first, and then I put ones at the end, because that way, if a solution becomes a fraction, I'm not always working with fractions. But in this case, since we already have a fraction, we're gonna continue working with it. Okay. But I'll show you another example. I would do this process until the end. All right, so now I have a 1 here, but now I want a 0 here. So all I have to do is add row 2 with row 1, and I'm going to get a 0. Okay, and that's the reason why it was not too bad on this one, because it's only one operation that I'm going to have to deal with a fraction anyway. So again, I'm getting a new row 1. My row 2 is not getting altered, so I'm going to leave it alone. I'm going to write it out first, but then I'm going to do the operation. So 0 plus 1 is just 1. 1 plus a -1 is 0. And the -1/3 plus 5 is going to give me a 14/3. So now let's do that. Let's just so you can see where I'm getting my values. Okay, so I have a -1/3, and I want to add that to 5. Yes, but in order for me to add fractions, I need a common denominator. So I would convert the 5 into a fraction, 5/1. And again, in order for me to be able to add these two, I need to have the common denominator. So my least common multiple between 1 and 3 is that 3. So to get a 3, I'm going to multiply a 3 to the numerator and a 3 to the denominator. So 3 times 1 will give me 3. I'm going to write it over. And 3 times 5 is 15. So now I can add these two fractions because I have the common denominator. So a -1 plus a positive 15 is going to give me a positive 14 over 3. And that's where I got that 14 over 3. Okay, so this was equal to 14 over 3. Okay, all right. So we solved our solution here. We see here we have our identity 1, 0, 0, 1. So that means that the x value is equal to 14 over 3, and our y value is equal to -1/3. Okay, so this is how we use matrices to solve for systems. Okay. All right. Oh, someone had a question?
You have a question.
I just saw that. It was me that typed it. It wasn't someone. I noticed. Thank you, Van. All right, let's solve for this matrix system also. Use matrices to solve this system. Now on this one, they were nice to us. They gave it to us already in its augmented matrix form, so we don't have to transform anything. So let's get to it. Okay. So since none of these two rows have a 1 to begin with, we're not going to do any interchanging. So we're just going to get a row 1, and we do want to get a 1 here. Now, again, I would only recommend to do this if you know, if it wouldn't give us fractions. But again, since the format here is going to work with fractions, I guess we want to practice working with fractions. So let's do this. So we're going to multiply a -1/3 to row 1, and that's going to give us a new row 1. And by doing that, if we see here, -1/3 times a -3 gives me a positive 1. A -1/3 times 4 gives me a -4/3. And -1/3 times the 22 is a -22 over 3. Yes? Now I have a 1 there. Okay, now what is it that I want? I want a 0 in that second row. Below the 1, in the row 2, column 1, I want a 0 there. So how do I do this? So what I'm going to do is I'm going to multiply -6 to row 1, and I'm going to add that to row 2. So again, I'm getting a new row 2. My row 1 is not getting altered, so I would write that out. I would write this 1 -4 over 3 equals -22 over 3, because I don't want, I'm not doing anything with that one. So I write that out first, so I make sure that I don't get confused on what I'm doing. All right, so now let's do it. Let's multiply -6 to the row 1. So when I do this, -6 times 1 is a -6, and when I add that to a positive 6, that is that 0 that goes there. All right, let's do it again. A -6 to the second element. So a -6 times a -4/3. So a -6 divided by a -3, that's a positive 2. 2 times 4 is 8. 8 minus 4 is going to be a 4. So that's that value that goes there. Row 2, column 2 is the 4. Got to do it one more time. I'm going to multiply the -6 to the -22 over 3. So again, -6 divided by -3, that's a positive 2. 2 times 22, that's 44. Plus a -28, so that's just a 44 minus 28, which is going to give me the 16. Okay. All right. So now I have a 1, 0. Now what do I want? Again, I want a 1 here, and I would do this one because again, this one is going to give me no fractions. So I'm going to do row 2. I'm going to multiply that by a 1/4. So row 2, again, I'm going to multiply 1/4 throughout. So again, row 1 is not getting altered. I write that out. That one's not changing, just leaving it alone. Again, I forgot my equal sign, but it's okay. So 1/4 times 0 is 0. 1/4 times 4, 1/4 times a positive 4 is 1. And 1/4 times 16. 16 divided by 4 is 4. And there's my new row 2. I'm almost there. I'm almost there at the finish line. Now all I want is I want a 0 here on this row 1, column 2 position. I want a 0. So how do I do this? I am going to multiply a 4/3 to row 2. And I'm going to add it to row 1. That's going to give me my new row 1. Okay, so again, my row 2 is already done. So I write that one first so I can make sure that I'm not changing anything with that one. not getting altered, so just write it out, 0, 1, 4. And I already got my solution, y is equal to 4, right? But let's get the x. So I'm going to do this operation, 4/3 times row 2 plus row 1 to give me my new row 1. So let's go ahead and do this. So 4/3 times 0 is 0 plus 1 is 1. That goes there. Okay, let's do it again. 4/3 times a negative 4/3. 4/3 times 1 is 4/3 minus the 4/3. That is the 0. That goes there. Row 1, column 2. Let's do it one last time. We're going to multiply 4/3 times 4, which is going to give us 16/3 minus 22/3, which is going to be a minus 6/3. That simplifies to a -2. -6 divided by 3 is that -2. That goes there. And we are done. So our solution here, since we have our identity matrix on the left of the equal sign, x is equal to -2, y is equal to that positive 4. Okay. So hopefully you guys are all having fun as I am, right? Okay, so that was section 8.1, just working with matrices. So now let's do 8.2. So 8.2, yes, I have one that said that loves working with matrix. So sorry, matrix operations. So for us to be able to add or subtract matrices together, they have to be equal. Okay. So one way that we know that two matrices are equal to each other is on their dimensions or on their size. So two matrices are equal if they have the same dimensions. Okay, so this is crucial for us when we're adding two matrices together. They have to have the same dimensions. Now, there's also something that we call a scalar multiplication to a matrix. So we can multiply a single number to a matrix, and this is called scalar multiplication. And to do this, we have to multiply that number to every element in our matrix. Okay, and again, to subtract two matrices together is the same as the addition. They have to be equal. And what does it mean to be equal? They have to have the same dimensions. They have to have the same size. They have to have the same number of rows with the same number of columns. All right, so let's go ahead and practice this. So let's say that we have these two matrices and we gave them names. We use capital letters to give the names of the matrices. So here, matrix A is equal to this matrix. Now, what's the size of this matrix? This is a 3 by 3 matrix. So this is a square matrix. When the number of elements, the number of rows equals the number of columns, it's a square matrix. This is a 3 by 3 matrix. B is also a square matrix. It's a 3 by 3, 3 rows, 3 columns. Okay, so let's do the first one, A. A says to do 3A. So this is a scalar multiplication to my matrix A. So what this means is I'm going to multiply 3 to my matrix A. But what that means is I'm going to multiply this 3 to all of the elements inside the matrix. Okay, so this means 3 times 2, 3 times 2, 3 times 4, 3 times the -3, 3 times the 0, 3 times the -1, 3 times the 2, 3 times the 1, 3 times the 2. Okay, all of the elements in the matrix. So our solution is going to be the 3 times 2 is 6, 6, 3 times 4 is 12, 3 times the -3 is a -9, 3 times 0 is 0, 3 times the -1 is a -3, 3 times 2 is 6, 3 times 1 is 3, 3 times 2 is 6. So this is the simplifying, right? We multiply each entry or each element in our matrix, and we simplify, we have our solution, right? So this was called this is an example of a scalar multiplication. Now let's do B. B says, let's interpret that as 3A minus B, or no, just do -B first. Let's do -B first. So that means this is also a scalar multiplication, but we're multiplying a -1 to my B. So this is what this means. The -B means I'm multiplying -1 to my matrix B, and it's just the same way that I did the A. I'm going to multiply -1 to all of my elements in my matrix. And when I do that, again, -1 times 2 is a -2, -1 times 0 is 0, -1 times 0 is 0, Negative 1 times a 1 is a positive. Well, negative 1 times a positive 1 is a negative 1. Negative 1 times a negative 4 is a positive 4. Negative 1 times a positive 3 is a negative 3. Negative 1 times a negative 1 is a positive 1. Negative 1 times a positive 3 is a negative 3. And a negative 1 times a positive 2 is a negative 2. Okay, so I have that. Now let's do C. C says, I want to add or subtract 3a minus b, right? So I already have my two matrices. I did the work, right? So 3a minus b means that I get my matrix 3a, the solution that I had there, which was this one, the 6, 6, 12, negative 9, 0, negative 3, 6, 3, 6. And I'm going to add it to the negative b matrix, right? Again, you can say it as a subtraction or as an addition. Since I already applied the negative, that's why I'm doing the addition, right? So I'm going to add these two matrices together. And again, the only reason why I can add these two matrices together is because they have the same dimensions. They have the same size. So the way we add matrices together is the same address with address. So for instance, what I mean with address is this 6, the first row here, 6, is in row 1, column 1. This 6 has to be added with the same element in the same address in the other one, the negative 2. The negative 2 is in row 1, column 1. So that's what I'm going to do for all of these. Each element is going to be added respectively. So 6 plus a negative 2 is going to give me a 4. 6 plus 0 is 6. 12 plus 0 is 12. That was a row 1. Let's do row 2. Row 2. Negative 9 plus negative 1 is a negative 10. 0 plus 4 is 4. Negative 3 plus a negative 3 is a negative 6. Let's do row 3 now. 6 plus 1 is 7. 3 plus a negative 3 is 0. 6 plus a negative 2 is 4. So I added all the elements corresponding to it, their position, and that's how you add two matrices together. Okay. All right. So now this one's copied right off your computer homework. It says, if possible, find a plus b, a minus b, 3a, and 3a minus 2b. Okay, we can do this. All right. So let's do the first one, a plus b. Now, what did we say? In order for us to add two matrices together, they have to have the same size. So what is the size of matrix A? So the size of matrix A is, let's see here, the first one is a 2 by 3, right? That's the size, row times column. So I have 2 rows, 3 columns. The size of matrix B is a square matrix. This is just has 2 rows, 2 columns. They are not the same. So since they're not the same size or the same dimensions, we cannot do this. So what we would put on there is impossible. We cannot add these two matrices together. Okay. All right. So I only did the first one, but let's go ahead. Then we can't do any of the rest. Since they're not the same size, I cannot subtract these two matrices together. But I could do 3a, right? I could do 3a. 3a would be just 3 times 6, which is 18, 3 times 0, which is 0, 3 times 4, which would be 12, 3 times a negative 3, which would be a negative 9, 3 times a negative 5 would be a negative 15, and 3 times 0 would be 0. That one I can do, but the others I can't do. That would be the only one that I could do, the 3a, because all the others, they're not the same size, so everything else would be impossible. All right. So let's have this one. Solve for x and y. So for two matrices to be equal to each other, they have to have the same elements in each. So here, I have a x, but the position where x is on the other matrix is a negative 3. So that is the solution for x. X has to be negative 3 because I have a negative 4 for the for the first row, second column. I have a 6 for the first row, for the second row, first column. But here for the y, for these two to be equal to each other, since I have a 21 on the left matrix, the y also has to be 21, yes? So the solution here for x and y, x is equal to -3, y is equal to 21. All right, so now here we have our second example is a little bit more complicated. They want us to do a little bit more work. Okay, for these two matrices to be equal to each other, they have to have the same elements in both. So we have an 18, 5, and x. But for this one, for the x here, we have 2x plus 5. And then, so for these two to be equal to each other, what we have to do is we have to do a little bit of algebra. So here, it says that x is equal to 2x plus 5. And then if I look at my second row, we have a 1, 2, 16, 1. But on the other matrix, we have a 1, 2. But for the third element, we have a 5y minus 4, and then 1. So for this one, 16 has to be equal to the 5y minus 4. So let's go ahead and solve for x. Again, on our matrix here is a little bit of algebra. We're going to subtract 2x on both sides. So 2x minus 2x is 0. X minus 2x is a negative x is equal to 5. So to solve for x, I'm just going to multiply by a -1 on both sides, or divide by -1 on both sides, however you like it. So x is equal to a -5. So there's one of our answers. Let's solve for y. To solve for y, I'm going to add 4 on both sides. So 16 plus 4 is 20, equals to 5y. To solve for y, I'm going to divide by 5 on both sides. 5 divided by 5 is 1, giving me that y. And 20 divided by 5 is 4. So now I have my solution. X equals -5, y equals 4. Okay. Now, hopefully I'm going a little too fast so I can finish going through the examples. I went a little too slow. All right, so how about this? Solve for x, okay? So says x is equal to 2a plus 2b. So first, since they have the same dimensions on these two matrices, I will be able to add them together. So I can go ahead and start the process. I first have to do 2a, and then the 2b, and then I would add them together. So first, let's add our constant multiple, 2 times the matrix A and 2 times my matrix B. So when I do this, again, I already did examples, so I'm not going to explain this. So we have our solution. Now to add these, again, we're going to add element with element. Since, again, they're the same size, I can do this. So when I add these two elements together, -6 plus 6 is 0, the 4 plus 4 is 8, the 6 plus -10 is a -4, -4 plus 10 is 6, 0 plus 0 is 0, 8 plus 6 is the 14. Okay. All right. How about this one? We have 4b is equal to -2x minus 2a. All right. So first, we can do additions of these matrices because, again, they both have the same size. They both are 2 by 3 matrices. Yes, the dimensions are equal. So the first thing we have to do for this is let's solve for the x, which is what they want us to do. So 4b is equal to -2x minus 2a. Again, if I move the 2x to the other side and the 4b to the other side, and then divide by 2, I have this. X is equal to -a minus 2b. So now let's do that. Let's multiply a -1 to matrix A, a -2 to matrix B, and then add them together, right? So let's do this. So let's do a -1 to matrix A, which is going to give me 2, -1, -1, 1, 0, -4. Let's multiply -2 to matrix B, which is going to give me the 0, -4, 4, -6, 0, -6. I'm going to add those two together, element with elements, okay? Position for position. So when I do this, 2 plus 0 is 2, -1 plus -4 is -5, -1 plus 4 is 3, 1 plus -6 is -5, 0 plus 0 is 0, -4 plus -6 is a -10. Okay, so this is how we do matrix operations. All right, now I think by the time, looks like I'm only going to be able to explain matrix multiplication. So the way we do matrix multiplication, we can't multiply all matrices together. They have to have a certain condition. Okay, so for us to be able to multiply two matrices together is that the number of columns of the first matrix have to be equal to the number of rows in the second matrix. If these two are equal, then we can multiply them. Now, this is just for your information, but the number of rows of the first one with the number of columns of the second one is going to give you the dimension of the product. Okay, so let's look at examples really quick. Okay, so if I want to multiply if I want to multiply matrix A, which is 4 and 1, this is a 1 by 2 matrix with a 2 by 1 matrix. I can do this, right? Because the first matrix has 2 columns, the second matrix has 2 rows, so this is the same. I can multiply them, and the resulting matrix is going to be a 1 by 1 matrix. Okay. So B, can I? So if I do this, the way we multiply matrices, skipping, is the same way that we said we found our size, the dimensions. It's row times column. So the way I would do this multiplication is row times column. So I would do 4 times 1 is the multiplication, and then plus 1 times 2 is going to give me that 1 by 1. So 4 times 1 is 4, plus 1 times 2 is 2. So 4 plus 2 is 6. So my answer is just 6. Okay. Again, we'll do some more examples on the multiplication. Let's do B. I can multiply these two matrices together because this is a 2 by 1 matrix multiplied with a 1 by 2 matrix. The columns of the first is equal to the rows of the second, and the resulting matrix is going to be a 2 by 2 matrix. Okay, so the way I multiply this is row times column. Okay, 1 times 4 plus 1 times 1, and then I do the second row. Row 2, column 1 is 2 times 4, and the 2 times 1. So when I get this, 1 times 4 is 4, 1 times 1 is 1, 2 times 4 is 8, 2 times 1 is 2. Okay, so let me just say something really quick too. Also, when you're doing the multiplications, it's telling you where the address is. So for instance, if I multiply 1 times 4, that's row 1, column row 1 with column with a column 1 of the first, so that's address 1 1. That's the 1 4. So when I multiplied row 1 with the 1, which is in column 2, right? Row 1, column 2, that's the address here. Row 1, column 2. Same thing with a 2. Row 2, column 1, that's address 2 1. That's going to go here, the 8. Row 2, column 2, that's address 2 2. That goes there. Okay. So this is how we do matrix multiplication. Let's do some more. So let's find a squared. And this one, we get a lot of questions on this one, on how to do it. And basically, a squared means that we just are going to multiply a with itself, right? So we have a squared is multiplying a times a side themselves. Now we can do this because they're square matrix 2 by 2. The columns of the first match the rows of the second. Okay, so let's go ahead and do this matrix multiplication. Okay, so again, this is a 2 by 2 matrix. My result is going to be a 2 by 2 matrix. All right, so let's do the multiplication. So the way we multiply is row times column. So we have 3 times 3 plus 1 times a negative 1. That is the address of the 1 1. Row 1, column 1 is this address 1 1. Okay, let's just keep on with the row 1. Row 1, column 2. 3 times 1 plus 1 times 2 is going to give me the position of row 1, column 2. Okay, now let's do the row 2. row 2, column 1. That's address 21. That's right here. So it's -1 times 3 plus a 2 times the -1. And then the last multiplication, row 2, column 2. That's address 22. That goes here. -1 times 1 plus a 2 times 2. And when I simplify, I have 9 plus a -1. It's going to give me an 8. 3 plus 2 is a 5. A -3 plus a -2 is a -5. And the -1 plus 4 is a 3. So this is how we do the matrix multiplication. I think I have time for one more example. Let's use up all of our time. I think I want to catch all of them, do all of it. So solve the following given the matrices below. So we have A is that matrix, which is a 3x2 matrix. And I have B, which is a square matrix, a 2x2 matrix. And it says multiply B times A. So again, the way that I multiply matrix B times A, can I do this? Well, B, the columns of B is a 2, but the rows of A is 3. These do not match, so I cannot do this multiplication. I cannot multiply them together. So now, let me ask you this. What if I had A times B? Would I be able to multiply those? Well, let's see. A, let me write my A is a 3x2 matrix. B is a 2x2 matrix. So if they would have told me to multiply A and B, that would have been possible because the columns of the first are equal to the rows of the second, and my resulting matrix would have been a 3x2 matrix. Okay. All right. Thank you all for joining me. Ms. Chuka, do you have anything to add for our? All right. Thank you all for joining me. Ms. Chuka, do you have anything to add for our students watching?
No, just next week, I believe is the final exam, and I know some of you are taking exam 4 next week, so we wish you the best, and we'll be here next week.
Thank you so much again for joining us. I hope to see you all next week to review for your final. Again, happy studies. Thank you.
Thank you, Mr. Carrizales. Thank you, Ms. Chuka, for your presentation. If anybody would like to download a copy of the presentation, you can go to the top right corner and click on the box with the arrow pointing down while the presentation is on the screen. We do want to remind you all of the previously recorded sessions, which are available on a YouTube playlist. This session will also be available on that playlist later today. Also linked was a short survey to help us improve our TVE session. So if you guys can please take a few minutes to fill out that survey, we would greatly appreciate it. Before you all leave, I want to share the TVE sessions that we will have next. At 1 p.m. today, we will have the presentation Learning Express with the EPCC libraries, and we will be back next week at 11 a.m. with the last Happy Math Hour of the semester, where Math 1314 and Math 1324 will cover final exam reviews. Our 1 p.m. session next week will be with the Tejano Mercado or Food Pantry with Campus Life. Thank you all for coming in today. We hope you all have a lovely weekend, and if you have any questions, feel free to use the chat box or your mic. We hope to see everyone again for Happy Math Hour.